Okay, let's dive straight in. Today we're looking at a paper called WorldGrow, Generating Infinite 3D World. And this really feels like a big step for generative AI.
Absolutely. It's tackling something pretty fundamental. How do you generate 3D worlds that are not just big, but truly continuous, infinitely extendable?
Which is, crucial if you want to build these large-scale world models, especially for embodied AI agents that need to learn in really open-ended environments.
Exactly. The core idea, the big innovation in WorldGrow, is moving away from trying to generate one massive scene all at once.
Right. They're using this hierarchical approach instead. It's all about modular block-by-block synthesis, and crucially, this coarse-to-fine refinement process.
Yeah, and it kind of rests on three main technical pillars. First, they had to adapt an existing 3D representation SLAT to make it, well, scene-friendly, as they call it, better for complex structures.
Okay, scene-friendly SLATs. What's the second pillar?
A smart 3D block inpainting method. This is how they actually extend the world, adding new blocks seamlessly based on the context of the neighboring ones.
Making sure the seams don't show, basically.
Precisely. And the third part is that coarse-to-fine strategy we mentioned. It uses two different levels of detail to make sure the overall layout makes sense globally while still getting photorealistic details locally.
And the results seem pretty impressive. They're reporting state-of-the-art performance, not just visually, but also in terms of the actual 3D geometry.
Yeah, on standard benchmarks like 3D front.
Huh?
And they've shown at scales they generated this massive scene, like 19 by 39 blocks, covering something like 1,800 square meters.
Wow. That's definitely big enough for some serious AI navigation tasks. Yeah. Stable, too, which is key.
Super key. Okay, so that's the overview.
Right. So let's unpack this a bit. Why is generating these huge or even infinite 3D worlds such a bottleneck right now? It feels like we hear about powerful foundation models all the time.
It's true, but think about what you need for, say, an embodied agent, a robot, or maybe an LLM interacting with a simulated physical world. They can't just learn in a tiny fixed box. They need space to explore and encounter novelty.
Without hitting an invisible wall after 100 meters. So the applications are things like advanced video games, VRR, sure, but really it's about these foundational training grounds for AI.
Exactly. And the problem is the previous ways of doing this just didn't quite cut it when it came to scale or coherence. They sort of fell apart.
Okay, so what were the failure modes? Let's start with the 2D lifting approaches, taking images and trying to lift them into 3D. What went wrong there when they tried to make big scenes?
Well, the geometry just breaks down. As you try to stitch together views or extend the scene, you get inaccuracies, weird distortions, flickering textures, aliasing. It just doesn't create a consistent, solid 3D world you could actually navigate reliably.
Right. It lacks that underlying continuous 3D structure. So what about methods that are native 3D? We have these powerful 3D generators now. Why couldn't people just stitch their outputs together?
Two main problems there: efficiency and, maybe more importantly, context. Things like implicit representations, NeurF and the like, they get really computationally heavy and slow when you try to scale them up to massive scenes.
Okay, so scaling is hard. And the context issue.
The big 3D foundation models, like the ones trained on huge data sets like Objaverse XL, they're mostly trained to generate objects. They can make a fantastic chair, a perfect lamp, whatever.
But not the room itself.
Exactly. They don't really understand scenes. They don't get how a room connects to a hallway, how walls should meet floors plausibly across large areas. They lack the architectural context, the structural coherence needed for a whole world.
Ah, so WorldGrow's insight was basically, stop trying to make one giant thing. Treat it like building with blocks. Leverage the power of existing models, sure, but adapt the fundamental representation for this block-based, scene-level task.
That's the core idea. They started with this thing called SLAT-structured latent representation, which came from an earlier work, Trellis. It's clever. It uses these latent feature vectors anchored at specific sparse points in 3D space to represent both geometry and appearance.
Okay, so SLAT worked well for objects.
Yeah, great for objects, but when they just tried to apply vanilla SLAT directly to complex, cluttered scenes like the inside of a building, they hit problems straight away.
You mentioned color bleeding earlier. What was actually happening there?
So imagine you have, say, a bright red sofa really close to a white wall in the scene. The original SLAT aggregated visual features like Dano V2 features using a simple projection method.
Okay.
But in a cluttered scene, the features from the red sofa could sort of wrongly project onto the voxel representing the white wall behind it, especially if the wall was occluded from that camera view. The aggregation wasn't smart enough about what was blocking what.
So the model would literally think the white wall was a bit reddish because the sofa was nearby, even if it couldn't see the sofa directly from that angle.
Yeah.
That would definitely mess up the realism.
Totally. It ruins the crispness and accuracy. So the fix was what they call occlusion-aware feature aggregation. Basically, they only gather features for a particular voxel from camera views where that voxel isn't blocked by something else.
Ah, makes sense. If the view of the wall voxel is blocked by the sofa, you just ignore the features from that view for that voxel. Cleans things right up.
Exactly. That solved the color bleeding and improved the surface accuracy a lot.
Okay, that handles the appearance fidelity. But there was a second problem with the original SLAT approach, right? Something about continuity at the block boundaries.
Yeah.
You mentioned floaters and artifacts.
Yeah, that was down to the decoder part of the SLAT model, the part that actually turns those latent features back into geometry. The original decoder, Dollars, was trained mostly on object data.
So it knew how to make the edge of a chair look right.
Right. It understood object boundaries, but it didn't really understand architectural boundaries, like how a wall should smoothly meet a floor, or how the edge of one generated block of the world should seamlessly connect to the next one.
So when you used it for scenes, especially at those block edges,
You got weird gaps or bits of geometry just floating near the edges. It looked disconnected, not like a continuous structure.
okay, so the fix seems obvious in hindsight.
Pretty much. They retrained the decoder specifically using scene block data, so it learned the patterns of typical architectural connections and boundaries.
And the ablation studies showed you really needed both fixes, the occlusion-aware aggregation and the retrained scene decoder.
Absolutely. You
Yeah.
needed both together to get that high-fidelity reconstruction quality within the scene blocks. Trying to generate worlds without fixing the underlying representation first just wasn't going to work well.
Okay, so now they have this improved scene-friendly slot representation. The next challenge is actually growing the world, adding new blocks infinitely. You said they framed this as 3D block inpainting.
Yeah, exactly. Think of it like this. You have the existing generated world, and you want to add a new block next to it. That new block is initially missing. The job is to inpaint or fill in that missing block based on the context provided by its already generated neighbors.
How do they guide the model to do that effectively?
They condition the generation process very explicitly. The input to the diffusion model that generates the new block isn't just random noise. It's a combination of three things concatenated together.
Okay, what are the three?
First, you still have the noisy latents, which is standard for diffusion models. Second, there's a binary mask, just a simple signal telling the model precisely which region is missing and needs to be filled in.
Makes sense. Explicit guidance.
And third, they feed in the actual known context from the neighboring blocks, but masked by that binary mask. So the model sees the noise, sees where to fill, and sees the existing geometry and appearance it needs to connect to.
That sounds like a really strong conditioning signal. It tells the model exactly what it needs to match up with.
It's very effective. It ensures the newly generated block is structurally and visually consistent with what's already there.
This leads us nicely into the coarse-to-fine strategy. You hinted at this earlier, this tension between capturing the big picture layout versus getting the fine details right.
Right. It's a classic trade-off in generation. If you use really large generation blocks, you might capture the overall structure better, like this is a hallway connecting two rooms. But you might lose the fine-grained detail, the textures, the small objects.
And if you use tiny blocks,
You get great detail, photorealistic textures, sharp geometry, but you might lose the forest for the trees. The overall structure might become incoherent, like rooms crashing into each other illogically. You lose the global context.
so WorldGrow's solution is to use two different scales.
Exactly. They have coarse blocks and fine blocks. The coarse blocks are wider, actually 4 times the area in the horizontal plane compared to the fine blocks. And they train a specific coarse generator, DWCSS, just to capture that high-level layout, room shapes, connectivity, major walls. Think of it as the blueprint generator.
Okay, so the coarse model does the architectural planning. Then how does the fine model come in? Is it a 3-step process?
Pretty much. Step 1. Use the coarse generator, DCSES, to produce the initial world structure, PCSES. This defines the basic floor plan and large structural elements.
Step 2.
Refinement. You take that core structure, you upscale it, and then you use it to guide the fine structure generator, AFUSESS. This is done using a technique inspired by SDEdit, a structure-guided denoising process.
So the fine generator adds detail, but it's forced to stick to the layout defined by the coarse model.
Precisely. It refines the geometry, adds details like furniture outlines, molding, sharper corners, but it cannot change the fundamental structure laid out by the coarse model. It preserves the global plan while adding local fidelity.
That sounds really smart. It decouples the layout planning from the detailed rendering. What's step 3?
Appearance. Once you have that refined, high-detail structure mask, you use the fine latent generator to synthesize the actual SLAT features, which represent the final appearance. The photorealistic textures, colors, lighting baked in, all consistent with the detailed geometry.
So structure first, refine structure, fine, then add appearance, fine. This hierarchical flow prevents weird situations like generating a really nice detailed couch that accidentally ends up halfway inside a wall because the structure wasn't fixed first.
Exactly. It ensures structural integrity throughout the process.
Now, for the actual block-by-block growth, how do they handle the transitions? Making sure block A blends perfectly into block B without any visible seam or weird overlap.
They're very careful about this. They use an overlapping context mechanism. When generating a new block, they don't just look at the immediate neighbors. They actually take a margin from the neighboring already generated blocks to use as context.
How big is the margin?
It's a specific fraction. A 38 tolera wide margin from the adjacent blocks, where $1 is the block width. This known existing data is used as the explicit context to guide the inpainting of the central 58 teller times 58 teller region of the new block.
So the transition zone itself isn't generated from pure noise. It's heavily conditioned on the real data from the block next door.
Right. That overlap ensures that the geometry and appearance flow smoothly across the boundary, making the seams essentially undetectable.
Okay, the whole system sounds intricate but logical. The real test is performance, though. How did it actually do on the standard benchmarks? You mentioned geometry metrics first.
Yeah, quantitatively, they showed state-of-the-art results on things like MMD COV and 1NNA, calculated using both chamfer distance and earth-movers distance.
Which, for people maybe less familiar, basically means?
It means the generated 3D structures are statistically much closer to the structures found in the real-world dataset, 3D frontier. The connections are better, the layouts are more plausible, significantly better than previous methods like block fusion or SimCity. The rooms look more like real rooms.
So the architecture makes sense. But what about just how good it looks? The visual fidelity.
That's where the jump is really stark, I think. They measured perceptual quality using FID Fréchette inception distance with several different feature extractors, and the scores were way lower, which is much better.
Like how much lower?
Well, for example, using CLIP features, their FID score was down around 3.95. The baseline they compared against, which was a fine-tuned version of the original trellis model, was way up at 13.17.
Wow, okay, from over 13 down to under 4. That's a huge leap in photorealism. For listeners, a lower FID means the generated images look statistically much more like real images.
Definitely. It really shows that the scene-friendly SLAT adaptations and that coarse-to-fine pipeline are paying off in terms of visual quality. The generated environments look much more convincing.
And is it practical? Is it fast enough to actually generate these massive worlds?
It seems pretty efficient, yeah. They reported generating a 10 by 10 block indoor scene, which is pretty large, in about 30 minutes. And they mentioned this is roughly 6 times faster than SimCity, one of the main competitors.
6 times faster is a significant speed up if you need to generate tons of training data.
Absolutely. And this speed, combined with the quality, leads to what I think is maybe the most critical experiment they ran, the stability test.
Right, because any generative system might look okay for the first few steps, but if you're claiming infinite generation, you need to prove it doesn't just fall apart after extending for a long distance.
Yeah.
Error accumulation is a killer.
Exactly. So they specifically tested the generation quality way out on the periphery, sampling blocks from the outer edge of a large $7 times 77 generated area far from the starting point.
How did WorldGrow hold up out there?
Remarkably well. The quality metrics, the FID scores, were consistent. They were comparable to the blocks generated near the center. It showed the system is robust against that kind of error accumulation and quality degradation over distance.
And the comparison. How did SimCity do on that test?
Not well. SimCity showed significant quality degradation at those distances and reportedly failed entirely producing incoherent or broken scenes in 70% of those long-run test cases.
70% failure rate. Okay, that really highlights the stability achievement of WorldGrow. That robustness is absolutely crucial if you want an AI agent to actually use these environments for long horizon tasks or planning. You can't have the world glitching out.
It's mandatory, and it also circles back to why those internal components were so necessary. The ablation studies really hammered this home.
What were the key takeaways from the ablations?
Two main things stood out. First, data curation mattered. They found they needed to clean the training data to remove implausible arrangements, like objects intersecting walls. If the training data has weird stuff, the model learns weird priors.
Garbage in, garbage out. Makes sense.
And second, it reinforced just how critical those tweaks to the set representation were. The visual quality metric, LPIPS, which measures perceptual similarity, only reached its best score, lowest value, when they used both the occlusion-aware aggregation and the retrained scene decoder. Taking either one out hurt performance.
So it wasn't just one magic fix. You needed that combination of changes to properly adapt the object-centric representation for complex scene generation.
Exactly. It shows the transition to world generation isn't trivial. It requires careful adjustments to the underlying models.
And they even showed some early signs of this working beyond indoor scenes.
Yeah, they included some preliminary results using the urban scene 3D dataset, specifically the Shanghai split. It suggested the core framework might be generalizable to outdoor cityscapes too, which is obviously a huge and complex domain.
Okay, so stepping back from the details, what's the big picture here? What does WorldGrow really mean for the AI field?
I think it provides the first really practical, demonstrably scalable, and stable framework for generating these vast, continuous 3D environments that people have been wanting for embodied AI training. It feels like we're moving past just generating isolated objects or small scenes into genuine world generation.
A foundational capability, really.
Yeah.
But it's not perfect yet.
Right.
The authors themselves pointed out some limitations in future directions.
Oh, yeah, definitely. The most obvious one is that the current system expands horizontally in the XY plane. It doesn't do vertical expansion, yet no multi-story buildings. Adding Z-axis expansion is a clear next step.
Crucial for simulating realistic buildings or cities. What else?
Dataset limitations are always a factor. Scaling up the quality and diversity of the 3D scene data, especially for complex outdoor environments, is an ongoing challenge for the whole field. Better data leads to better generation.
And they also mentioned semantic control, right? Right now, it generates plausible scenes, but you can't easily tell it what kind of scene to generate.
Exactly. The current system is mostly unconditional. The big next step is integrating semantic guidance, perhaps using large language models. Imagine telling it, generate a 3-bedroom house with a modern kitchen connected to a cozy living room, and having it generate the layout and style accordingly.
That kind of high-level control would make these generated worlds incredibly versatile for targeted training scenarios. But even without that yet, the core achievement of stable, scalable, coherent generation is huge.
It really is.
Which brings us to maybe a final provocative thought. If tools like WorldGrow continue to improve, and we can generate these incredibly vast, detailed, navigable virtual worlds basically just using compute,
Right.
how long will it be before the fidelity and scale of simulations start to make collecting real-world data for training general AI agents seem, well, maybe inefficient or even obsolete for many tasks?
That's the million-dollar question, isn't it? How much of reality can we effectively simulate, and is simulation the ultimate path to AGI? A fascinating question for the future.
Indeed. Okay, that was a deep dive into WorldGrow. Lots to think about there.